Hi everyone, thank you so much for joining us today. My name is Anya. I am a student recruitment and outreach officer at the University of Reading. And today we have a really exciting talk from Mike Lockwood from our Department of Meteorology. And yeah, I'll pass on for Mike to introduce himself. Please send in questions as we go along, and I'll be able to relay them to Mike, and we'll be able to answer them at the end. So there will be time at the end for questions, but feel free to send them in as we go through the presentation. Mike, over to you.
Thank you, Anya. Good afternoon, everybody. Yes, I'm Mike Lockwood. I'm a professor here at the University of Reading in Space Environment Physics. And at the moment, I'm also president of the Royal Astronomical Society. And what you're watching here was a night on Orkney where the aurora was quite spectacular. I shall explain more. Okay, so I'm going to talk about great auroral events. So what is aurora? Well, it's lights in the sky. And why is it called aurora? Let's start with that. Okay, and like a lot of these things, it goes back to the ancient Greeks, because the ancient Greeks had a goddess of dawn. She wasn't called Aurora, she was called Eos, and she rode through the heavens with her on her chariot with her winged horses, and she would sprinkle light over the world as she went, and she did this every day, of course. And that's quite a nice idea, and so the Romans borrowed her. The Romans borrowed a lot from the Greeks, and just to make it theirs a bit more, they renamed her. They called her Aurora instead of Eos. And then people looking for the aurora would quite often think it was sunrise until they realized that actually it was sunrise coming from the north and not the east as it should be. And so the name Northern Dawn, or in Latin Aurora Borealis, became common in Northern Hemisphere use for the aurora. But then we realized that aurora wasn't just in the Northern Hemisphere, and people who lived in the South knew, but when explorers like Captain Cook saw aurora in the Southern Hemisphere, we realized it was a phenomenon around both poles. And actually, this is an hour of movie here from a NASA satellite called Polar, and it was observing from just about the equatorial plane, quite a long way from Earth. And so it could see both auroral ovals at the same time. And actually, if you notice that it's only an hour of data, but you'll see that the aurora brightens simultaneously in north and south. So they're very much connected, the aurora in the north and the south. And if we're going to call the Northern Hemisphere one Northern Dawn, we've got to call the southern one Southern Dawn. And in Latin, that's Aurora Australis. So that's where the name comes from. Where do the lights come from? Where does it what's actually emitting up there? Well, it comes from very high in the atmosphere. We're talking 120 kilometers and up. And at those heights, the dominant constituent of our atmosphere is oxygen. I should say this is well above where the troposphere, where we get all our weather. At the very top of that is below 20 kilometers. So we're talking hundreds of kilometers here. So atomic oxygen dominates for much of the region. At the very bottom, molecular nitrogen, which you can see here in the green trace, takes over. And at the very top, helium takes over. But for most of the upper atmosphere, as we call it, which is really the lower edge of space, it's atomic oxygen. So what's making the atomic oxygen glow like this to give us the lights? It's not always atomic oxygen, I should add. The answer is actually energetic electrons, and electrons being charged, they tend to move down field lines. So I'm going to put an electron on this field line here just before it precipitates down into our atmosphere. Now the chances are it's going to meet an oxygen atom somewhere on its journey. Let's put it there. And what happens when it hits the atom is that it excites it. What it actually excites is an electron inside the atom to a higher energy level. I'm going to make the atom throb to show it's in an excited state. They don't actually throb like this, but that's how I'm going to show it. And after a while, it de-excites again. And when it does that, well, let's see. So there it is, it's excited, it de-excites and produces a packet of light, a photon, an individual light particle. Light is a wave, but it's also a particle, and individual quanta of it are called photons. And for this energetic electron hitting a quite low altitude oxygen, it's a green light that the atoms emit. But then let's take another field line and another electron. This one's not as energetic. It's not going to penetrate as deep into the atmosphere. So if it does collide, it's going to collide with an oxygen quite high up. It's not going to excite the oxygen to such a high level. And again, it excites. Now, what's interesting is that this actually takes, in real life, 2 minutes before it de-excites on average. And when it does, it produces a red photon. So we have an understanding of why we quite often see green aurora with red on top of it. The green's coming from more energetic electrons that penetrate lower down, and the red's coming from lower energy electrons that can't penetrate as far. Now, that green and that red line, turns out there are lots of emission lines possible, particularly if you fold in the other potential atmospheric gases, like the blues tend to come from molecular nitrogen and things like that. So there's a whole spectrum of different colors that you can get because of the different combinations of energetic electron energy and atoms or molecules to hit. And you can see what I was talking about the red being above the green rather beautifully in this picture from the space station. Okay, you can actually see the red sitting right up to about 600-700 kilometers altitude, whereas the green is focused around 120 to 150 kilometers altitude. So now this is the difficult bit. I promise not to do too much difficult physics, but I'm going to get it out the way early on. So this is our magnetic field, our magnetosphere, we call it. It's the area of space dominated by our own magnetic field. And it sits in, it's very often said that the electrons that cause the aurora come from the sun. That actually can be true, but it's more often not true than it is true. Okay, so what we do get is we get low energy electrons and ions together coming from the sun in what we call the solar wind. It's a continuous outflow from the atmosphere of the sun. All stars do it. All stars have a stellar wind. So here it comes. It's supersonic, and so when it hits the obstacle that is Earth's magnetic field, a bow shock forms, just like the shock ahead of a supersonic aircraft, and that slows it down. Okay, so it's still the solar wind, but it's slowed behind the shock. Now, brings with it, and I don't have time to explain what we call the frozen in flux theorem, but there is a theorem that shows that it will bring with it any magnetic field when it left the sun. And so a field of solar origin that's made inside the sun by the solar dynamo reaches us, and I've drawn it pointing southward here because that's actually the most interesting orientation. It can have any orientation. So what happens is that when we get to the bow shock, it's slowed immediately, but of course, where it's still out in the solar wind, it keeps on going. And so progressively it gets what we call draped over the nose of our magnetic field, of our magnetosphere. And why the southward field is so interesting is that it's meeting a northward pointing field of the Earth. At the moment, magnetic field comes out the south pole of the Earth, round and then back to the North Pole. That can change. We do get paleomagnetic reversals, but they happen on geological timescales, so we're not going to worry about that. So when they're anti-parallel like this with a southward field, the most important process in space physics can take place. And what happens is the fields, instead of being parallel to the boundary, they thread it. And so like that. Okay, so suddenly we have field lines that are connected to interpret into the solar wind that are inside our magnetosphere. And now an electron, a low energy one, can get in, and because it's low energy, it produces red aurora. And we call this what we call the cusp region. And similarly, in the southern hemisphere, that too is open like this, and we get a corresponding aurora there. Now, some electrons that get in this way follow a trajectory rather like this. They can bounce near the Earth, and they end up here in a region we call the plasma sheet of this tail. It's like a long comet-like tail that the solar wind has deformed our magnetic field into. And there they get accelerated. They get accelerated from processes we don't fully understand yet, but we do know the energy is the energy that was extracted from the solar wind flow. And they get accelerated back and hit the atmosphere and make it glow, okay, in both hemispheres. So we have this process going on, and that's electrons coming in. But as I said, more often, the electrons, particularly during disturbed times, have come from our own ionosphere, the ionized upper atmosphere. And they make their way up field lines into the same region, but then suffer the same acceleration, and we get green aurora. And that's the more common way that night side aurora occurs. And this is a diagram that's just in the noon midnight plane of the Earth. Of course, it should be three-dimensional. We should go over towards dusk and towards dawn as well. And when we do, we find this plasma sheet actually envelops, goes all the way around. And so the aurora, this is the section of it just at midnight, but actually it forms a continuous ring around each pole. And actually, they tend to be mirror images of each other when we draw them like this, because in the top diagram there, we're looking down on the North Pole of the Earth. And in the bottom diagram, we're looking down on the South Pole of the Earth, which of course is in the opposite direction. And so the aurora is flipped like a mirror image. Okay, so that's where we are. This ring right around the poles is very, very variable. So when the amount of energy extracted from the solar wind is very low, the aurora tends to be dim, the ring tends to be quite thin in width and small in radius. And that means the aurora, like in this picture here for low activity, is actually somewhere poleward of the North Cape of Norway, okay, up there in the Arctic Ocean. But if the amount of if amount of energy picks up, then we can start to see the aurora at middle latitudes, and it comes down to the middle of Scandinavia. The band thickens, and this happens because the radius of the ring has increased, so that's moderate activity. And then if we get very high activity, we start to see it almost too far south for Scandinavia, but into Scotland or England. And in this image on the right, by the way, is a mixture of infrared and ultraviolet light. And so you can see the city lights. And so, for example, this is San Francisco here. Oh, sorry. And here's London here. And this is Tokyo. So you can see the aurora forming this continuous ring. And what's happening is the ring is expanding in radius and bringing it down to us. So where it's a rather rare event that we see aurora, if you were in the north of Norway, that's the normal situation. And what's happened is if it's with us, it's not at the north of Norway, it's migrated south. So there's a sort of there's a perfect anti-correlation between us seeing it and the north of Scandinavia seeing it in the European sector. So there are lots of different forms to aurora, but actually it turns out to be simpler than you think. This on the top but left here, you see what we used to call an arch in Old English literature. It's now, we call it an arc nowadays. And the form on the right is what we call a coronal form, but actually they're exactly the same thing. If I was stood underneath the arc, underneath the arch there, looking up the field line, I would see it as a coronal form. So they are actually the same thing. It's just a different viewing position. And in the bottom here, you have a double arc structure. You can see the red above the green. And when if that went overhead, we got this sort of picture, and you can see the green is actually, you're looking up the field lines, the magnetic field lines, and the green is on the outside because it's lower. And as you look higher up, you see the red in the middle. So that fits. So that is what the picture on the left looked like when it went absolutely overhead. But there are other forms of aurora. At mid-latitudes, we tend to get this rather diffuse red glow. And the red tells us it's lower energy electrons than the green. We need to explain where they're coming from. I'll get to that. So I want to introduce a survey we did. This was after the events of May last year, which was the first really big event we'd seen for a long time, a good 30 or 40 years since we'd seen something of that scale. So we had a look at the whole of 2024, and we found 4,735, not actual sightings, what with the samples we call them, because we tend to group sightings together if people are close together. I'll explain the radius we use in a bit. But if they're within about 25 kilometers of each other, we count it as one sighting. Otherwise, you'll come to the conclusion that aurora mainly happens over cities because there are more people there to observe it. Okay, so that's how we kind of allow for that factor. The mauve dots in the top diagram here are where, sorry, stop doing that, where we observed aurora during 2024. And the black dots are from a survey that went all the way back to 1650. That's 1/5 of a million of these area combined samples that we took. And you can see, for example, we didn't get many in May in 2024 from Russia. There don't tend to be so many. They've since the rural tourism there became less popular, then we don't get many such samples from there. And you'll also notice the Atlantic, the shipping routes. We used to get a lot in captain's logs recorded, but nowadays they don't bother. So we don't have many in mid-Atlantic there. And you'll see a distinct correlation with where people live. If the bottom map is a map of population, and until you get to very low latitudes like the subcontinent, where there are a lot of people, obviously, but not much aurora. But there is a very distinct correlation between population levels and the number of auroral sightings you get. Now, I just need to explain the lines of constant magnetic latitude that were on those maps. They're shown again here. This is geographic latitude against longitude, and the contours are magnetic latitude. And this is a map of electrons precipitating made by a spacecraft. It takes about a day to build up a map, but although there are several, it's about a month's worth of data in these maps. And you can see two types of aurora, and the top one was before a storm. Sorry, two types of precipitation. One is sitting in an auroral band in the south and one in the north here. And then there is this big precipitation here. These are more energetic electrons, and they're coming down through a rather weak point in Earth's magnetic field called the South Atlantic Anomaly, which, again, I'm not going to talk about too much. The dots here are where we saw aurora in the same month that the map was compiled. This was for a month, that's the month immediately after that, when there was a big magnetic storm. And you see the auroral oval is, particularly in the south here, very enhanced, more auroral sightings, but again sitting in this band of the auroral, what we call the auroral oval. So this magnetic latitude works very well organizing the aurora, and that's quite important. So here's a look at 2024. Here are where our area combined samples of aurora were. Okay. This is the statistical thing for the whole data set right back to 1650. So it's most likely to be in the dark gray. You'll notice here in midsummer, we can't see it at high latitudes because of sunlight. Very, very rare to see aurora during sunlight. And so when in the 24-hour daylight of the summer at high latitude, you don't see it. And actually the number of hours you have to see it, even down here, goes down in summer, and so recordings get less common. Okay, but you can see these big events. Now, this was the 10th of May event, And there was one in August and then one in October. And then right on New Year's Eve, there was another one. Okay, so these big events. And in the bottom, we have an index of how much Earth's magnetic field is being shaken around by the solar wind. And you see these big spikes. These are what we call geomagnetic storms. And you see a very strong correlation between the geomagnetic disturbance level and this low latitude aurora. We call these geomagnetic storms. And this association between low latitude aurora and geomagnetic activity was made first about 100 years ago. It was very contentious. People didn't believe the sun could be having an effect on both, but that's the way it turned out. So how does the sun have an effect? Well, these are predictions that were made by my colleagues here at Reading, Matt Owens and Luke Barnard. They run a continuous prediction service that's available on the web for what we call coronal mass ejections. These are emitted by the sun, and they're the cause of these big storms when they hit the Earth. They travel faster than the normal solar wind. So if I run the prediction, you can see there's this rotation of the sun and the solar atmosphere that gives everything rotating. But then these events come out. The first one missed the black dot, which is the Earth. But then we had a whole sequence on 10th of May 2004 of 7 events buffeting the Earth one after another. Now, as I say, these were predictions made before the events actually hit. So they're worth actually seeing again if I can. No, it doesn't want to. There we go. So one event comes out here. That's going to miss the Earth, no problem. And it's not very severe. But these are very strong events, a whole series of them, and coming and hitting the Earth. So we make these predictions. We actually fold in data to update them. We get probabilities of certain impacts because we can make so many predictions. And this was a spacecraft just up from the Earth. You saw the field increase when the event is hit. The velocity picks up. The pressure of the solar wind goes up. And then this is the terrestrial response. So we can predict these things quite well now, but only on short time scales. We don't get a lot of time warning time. So let's take a look at the event of 10th of May. This is a picture from space again, and it's actually picking out where the aurora is dominantly green. But if we look at the purple dots, which are where we saw aurora from the ground that night, then you can see that we see aurora considerably equatorward of that ring. So if I take this first image here, this is Ontario, Canada, where there was nice green aurora and it's in the ring. The next one, this is a place some of you may know. It's Silbury Hill in Wiltshire, and quite close to Stonehenge. And you can see red over green with a bit of nitrogen blue in the middle there. And that's right on the edge of the band of the aurora seen from space. If we come further south, this is in Hungary here, we can see some red over green, but there's not much green. And then this is the Superstition Mountains in Arizona. And we can see a hint of some green at the lowest altitudes, but it's largely a mixture of oxygen red and nitrogen blue. And then one of the lowest latitudes where aurora was seen, or not the lowest, was down here in, this is Santa Cruz de Tenerife, and you can see this red glow on the northern horizon. Okay, and that was one of the most equatorward observations, but well equatorward of where the spacecraft is detecting the auroral oval. We can see the electrons that are causing this. This isn't actually from that date, this is another day. But so we had a spacecraft here that was in the southern hemisphere, equatorward of the auroral oval, and it flew like that across the auroral oval into what we call the polar cap in the middle of the ring there. And with time, and it's plotted here as a function of magnetic latitude and energy going in the vertical direction, and this is the flux of electrons that you're seeing. So we can equate this with what we actually see. So for example, we're getting green aurora from these energetic electrons here. Okay, and that's the main auroral oval ring that you can see. But here we're only getting very low energy electrons, and that's the diffuse red glow. Okay, And then here we can only see the diffuse red glow, and it's north over the horizon. But then in here we've got some quite energetic ones, and although it's well over the horizon, we can see green and a bit of red. Okay, so, and this picture was actually taken from Oman, which is the first time auroras have ever been seen in Oman. And you can see the northern dawn idea. Okay, it looks like dawn on the horizon, but actually it's coming from the north. So where are these low, these electrons coming from that are inside the main auroral oval? So here are the field lines that are coming in from that plasma sheet with the accelerated electrons, giving us nice green aurora at high latitudes. There is this population, they're trapped in Earth's magnetic field of very energetic ions and electrons, and we call them the radiation belts. They were the first part of space to be detected. And when we get a storm, they move in towards the Earth. And they come into a region that we call the plasmasphere, where there are these nice low energy electrons just minding their own business, but they get knocked down in the field lines into the atmosphere. And so down they come, and they give us the red glow on their own. Okay. And sometimes we can be in a position like here, and we see red above green, but actually they're not on the same field lines. That green is much further away than the red. Okay, and so this is because this is so much higher than the green. They look like they're on the same field lines, but a lot of it's not. But sometimes we do get high energy electrons and low energy electrons coming down the same field line like this, and we clearly see on the same magnetic field line red above green. So we can really explain an awful lot of the auroral morphology that we see and the variation. A few more notes about aurora at high and low latitudes that's interesting. You get much better colors at low latitudes. I think it's because everything's a bit more spread out. At high latitudes, it's much more structured. It's much less diffuse. It's much more structured. It's much more dynamic. It moves around much faster and more dramatic ways, but it tends to be green. It tends to be the dominant color is green, and with sometimes a bit of purple from the nitrogen along the bottom hem of the curtains. But it's nothing like the colors that you get at low latitudes. So it's not as dynamic, but it's more colorful at lower latitudes in general. And on the night of May 10/11, we had some wonderful pictures that appeared in the media. The one here is on the right is St Mary's Lighthouse in Tyne and Wear. And the one on the left makes me laugh. It was from the Gower Peninsula. Most people, when aurora appears, they rush out to try and get clear skies to get a better view. This guy rushed into a wood to take this wonderful picture with the trees silhouetted by the aurora. So it's a brilliant picture, but it goes against one's first reactions. Now, this survey we did that went back to 1650, we were very interested in just looking at ancient reports of low latitude aurorae. And there are some very ancient reports. They tend to be, certainly from this country, mixed up with descriptions of dragons and things like that. But this one that I'm interested in here is actually in the Bible. It's in Ezekiel. And we can date it because the same event was seen on the 12th of March, 567 BCE by Assyrian and Babylonian astronomers. And we think, and it's a perfect description of Ezekiel of what a red coronal overhead form. And he was, we think in Nippur, which is in modern day Iraq. And in fact, it's a major archaeological site. This is a picture of Nippur under archaeological studies. But it's very long way south, 41 degrees. Is this plausible? That was one of the questions we wanted to look at in more recent data. So since we started the study, in the 400 years that we're studying, things have changed a lot. Okay, a lot of things have changed in 400 years. And firstly, the motivations and the nature of observers. And by observers, I mean people who have the wherewithal to record that they've seen it. The size and distribution of the world's population, and that too has tended to increase the number of sightings that we get. Okay, so the upward arrow means more sightings a result. The magnetic latitude of major centers of population has moved. I'll talk about that in a moment. And that can work both ways. It can take the aurora away from a lot of people, and it can take it towards more people. So that could work either way. We now have digital cameras, particularly on mobile phones, has increased the number of sightings enormously. We have people know what to look out for and how to observe it much better than they used to, so that helps. We can give them forecasts to help to plan their observations, so that helps. We have the internet to disseminate observations quickly, and that helps. We have auroral tourism. A lot of people travel up to high latitudes to see the aurora, and that increases the number of sightings. They put all their pictures on social media. We have citizen science projects that get people out observing and recording. And then the one negative thing is light pollution. So night pollution, which seriously hurts your ability to actually see aurora. So it's nearly all positive, but there's a big negative there. So who does this observing? Well, that's interesting. It's changed over the years. It used to be doctors and clergymen. I'm amused. The two I've chosen here, the doctor on the left is a guy called William Huxham, who was in Plymouth, believe it or not, recorded the aurora very frequently. Seems to have been a terrible doctor. His patients nearly all died, but he did write a classic book on fevers. So he's obviously a theorist and not practical. On the right, you have a clergyman. This is the Reverend Clouson from the Shetland Islands. And he's there because he's recorded the aurora more than any other person in history. There are 870 nights, I think, on which he recorded the aurora. It moved from them to gentlemen scientists. The one on the left is called Edward Lowe, and I mention him only because he had this wonderful, huge white beard. And so his nickname at the time was the giant snowflake, which has different connotations today, but are rather like that. And then lighthouse keepers. I'll explain why in a bit. And then it moved to professional observers. On the right there, you can see a former colleague of mine, Betty Lanchester. And on the left is Shin Akasofu and Sidney Chapman, two very famous early space scientists. And now we've moved to spacecraft observations, so robotic spacecraft, and the public through citizen science and social media. So things have changed a lot in terms of how, and a lot of them used to be reported, the gentlemen scientists and the doctors, they would report it in newspapers. The lighthouse keepers, well, that's an interesting story. Where did that come from? It comes from a bombing raid in the First World War, believe it or not. Initially, Britain had an agreement with Germany not to bomb the Berlin or London because the royal families lived there. And of course, it was us who broke that agreement. We bombed Berlin. And so the Germans retaliated, and they had these huge biplane bombers, the Gophers, they were called. Unfortunately, they didn't have good navigation, and they did actually bomb Bury St Edmunds, thinking they were hitting London at one stage. The navigation was that poor. And we mounted air defences, but we didn't bother at New Moon because it being dark, they couldn't find their way at all. But on the night of 7th, 8th of March, 1918, some planes got through to London. It was new moon, it was dark, but there was aurora, and the aurora lit up the Thames, and they followed that, and they dropped their bombs on London, largely hitting Lords. So really not cricket at all, quite frankly. But yes, I think it was actually quite sad. There were about 15 people killed. But that was really the only successful bombing raid of London. And it was made possible by the aurora. And so the Air Ministry employed lighthouse keepers to record aurora and telex it through, send a telegram as soon as possible from the air defense point of view. And so we got sightings of aurora from all these lighthouses around the coast of Britain. And it's a very plentiful source. Right up to the 1950s, they were recorded in Air Ministry documents. Now, I mentioned that the magnetic field has changed a lot. So this shows 3 magnetic latitudes, include 4 really, because the points are the pole and 90 degrees, and how they've changed over the period that we were studying. From in blue is 1650, and the dark red is today. And the map on the left is looking down on the pole, a polar map, and it's a Mercator on the projection on the right. And you can see that the changes, particularly at low latitudes, in magnetic latitude, are quite considerable, particularly in the European and Atlantic sector. But in the American and Pacific sector, they're really quite small. As it happens, it's just how the poles happen to have moved. So that's had its effect. For example, in the UK here, I mentioned that William Huxham recorded the aurora in Plymouth many times. And that's because Plymouth, which is the purple line on this graph, sat in the main auroral oval. And it was one of the best places to study it, as was London and King's Lynn. But slowly, the magnetic latitude of these places got smaller because the magnetic pole was moving away from us. And so we became subauroral, and Plymouth is now not a good place to see aurora on a regular basis. And whereas the Faroe Islands were too far north initially, they've become a good place to see the aurora. They now fall in the auroral oval, which has moved across the whole of Britain, including Shetland and Orkney, right up to the Faroe Islands. So it matters where you can see things, okay? And things have changed in just the period of our study. And so we have to allow for the change in the magnetic field when we're comparing observations from a long time ago. The other thing I want to just mention is the effect of mobile phones, because firstly, they give us contact with social media, so we can instantly post pictures of aurora. And on the other side, you have this wonderful device. You have this wonderful auroral detection device called a camera. Now, people think that the cameras are making things up because you can see things that you can't see with the naked eye. It's actually very complicated. And the human eye is a remarkable thing. And if it's properly adapted to the dark, it can see individual photons. The brain wants about 12 to 20 photons before it makes up its mind what it's seeing, but the eye is detecting individual photons. The thing is, though, it only detects it in black and white. You don't get color and night vision. It's an evolution thing, really. If you were attacked at night by a tiger, you didn't particularly care if it was a red tiger or a blue tiger. What you wanted to know was how big it was and how fast it was moving. And so motion and size are well recorded, but color is not at night. So people say, oh, the camera was making up colors. No, the camera is telling you the truth. The camera is accurate. It is your eye that is not able to see the colors. It can see the aurora, but it's always a bit white and gray, okay? But the colors come out in the camera, but that's the reality, not what your eye is telling you. So the camera is actually a better device. But in terms of absolute sensitivity, provided you've kept your eye in the dark, and that means not looking at your camera for about 2 hours, then your eyes will be as sensitive as the camera. One of the problems we have is, for some reason, people love faking auroral pictures. The original fakes were what I call light painting. This is dead easy. You put some fairy lights on a fishing rod and wave them around in front of a camera with a long exposure. And so these pictures, you'll see them frequently on the internet, and they're all faked nonsense, quite frankly. And we even know how it's done. Recently, we've had another problem with AI. This was an early AI picture of the aurora. It's all wrong scientifically, but it's going to get better. We're aware of that. They also haven't got any reflections in the field, which is wrong. So there are normally clues, but as AI gets better, it's going to get harder and harder to tell. And then a particularly difficult type to detect is what we call recycling, where you've got a genuine picture of the aurora, but you're claiming you saw it last night and from a certain place. Why we know this is recycling is that on the 10th of May 2024, sadly, the sycamore tree wasn't there anymore, thanks to the idiots that chopped it down. And so you know that was a fake. Okay, but identifying fakes is unnecessary, but an annoying, but it is a problem. And then we need to know where things are. Sometimes people just say England. Well, that's not very helpful. Okay, so when it's over a well-known site, that helps a lot. So I know where this is. This is Gateshead. No doubt about where that one was. I know where this one was. This is Anthony Crosby's Men on the Beach at Crosby. And so again, an identified location. Observatory Hill, Edinburgh. Yep. This one that amuses me. This is the Ring of Brodgar in Orkney. And I contacted Anne-Marie and said, why are the stones blue? Thinking we might be onto something about the blue stones in Stonehenge or something, some link that had never been discovered. And she said, ah, yes, a police car was passing by at the time. So that's why the stones are blue. It's an ancient ring, about 3 times older than Stonehenge. Well-known historic sites, Silbury Hill in Wiltshire at Avebury and Stonehenge. So again, we can identify exactly where these were taken. And if you're in the field, you know where these are taken to. These are taken by a guy called Alan Flett in Orkney. And the aurora there is so common that he doesn't bother to go outside to take pictures. He takes it from his kitchen window, which means his washing line appears in every picture. So his famous washing line tells you that that's taken from Orkney, we know. Okay, I mentioned the auroral ring. How am I doing for time? Okay, nearly there. If we take a typical height, it turns out observers that are within about 25 kilometers of each other will see the same aurora. So we tend to take areas, circular areas that are 25 kilometers in radius as being just one sighting and put them together. And that actually means so everything inside the M25 basically would be just counted as London. Okay, there's no point. They were the same. Otherwise, you just get a lot of reports from London, and because there are a lot of people there. Incidentally, when I put this together, I was quite delighted there were so many traffic jams on the M25 because it made the ring show up as a nice red ring, but I don't suppose it was as nice for the people that were stuck in the jams. Solar cycle, we know it goes, the low latitude aurora is much more common when the sunspot activity is high. This plot also shows that there's a bit of a diurnal annual variation, and that the equinoxes are favored for big auroral events. We know why that is. I just don't have the time to explain it to you. It's called the Russell-McFerrin effect, but it's rather wonderful. It predicts things rather beautifully. So we know it goes up and down with the activity of the sun. And then this was the result of our survey going right back to 1650. So at the start there, we were in a period that was called the Maunder minimum. There were no sunspots recorded, despite the fact people were looking. Aurora was very uncommon and normally at quite a high latitude, magnetic latitude. The event on May 10 that I've been talking about was this one. And you can see it's historic. It reaches down, it's the 3rd lowest latitude it's reached that we can find. This is the lowest latitude. It was on 4th of February 1872. And this is the famous Carrington event that started it all. The first time we actually saw this sort of phenomena occurring, although there was a lot of debate about exactly what had happened. This was compares the May event. There's a sunspot group that caused the May event in 2024. This is Carrington's drawing of the sunspot group that caused the storm he saw. This is a modern index of geomagnetic activity. And then this is a reconstruction from what magnetic data we have during the Carrington event. And the thing that marks it out is this huge spike that we didn't get in May. And we still don't know why this happened, but it had enormous effects. And one of the big effects was on telegraph systems because, oh, yeah, sorry, just to finish. Here's the May event seen in modern cameras. These kidney-shaped regions here are Carrington's white light flare that he saw. Okay, this is the first time one had been seen. We didn't see another one for another decade, and the third one took another decade after that. Those flares also emit X-rays, and they caused a little signature in the magnetometer 8 minutes later, which is how long the light from the flare took to reach Earth. But then nothing happened, but the CME was traveling, and the CME hit here. And the geomagnetic storm was so great that the trace went off scale for several hours. The big effects of this were to the early telegraph systems that ran along the railway lines. And here's this is a picture from 1875, so a few years after the Carrington event, and you can see these telegraph lines in the picture. And the currents that flow in the ionosphere that give you the geomagnetic storm also induce big voltages in long lines, particularly for lines that are north-south oriented. Sorry, east-west oriented rather than north-south. And these voltages, the Morse code operators, when they made contact, they got an electric shock that sometimes threw them across the room during the Carrington event. But it wasn't the first time it had happened. The first space weather event we know was again on the railway telegraph system in 1847, and it was seen on the Midland Railway. That was the first ever what we call space weather event. And this matters today, but it can cause disruption to power grids. It can cause problems in pipelines, all sorts of things that you have to worry about with the induced currents caused by the aurora overhead. Okay, so let me go back. I'm going to finish off with a summary. I'm going to finish off with a league table. So top of the league table for the lowest latitude at which aurora was seen is 4th of February 1872, and we have verified reports from Khartoum in the Sudan. The Carrington event was actually the precursor to the Carrington event was seen right by a ship docked at Panama City. And then the third was May 2024, when it was seen down in Oman, and I've showed you the picture of that. So it gives us a way of taking a look, and it does mean that Ezekiel's aurora in modern day Iraq was entirely possible. And with that, I think I'll stop and take any questions.
Thank you so much, Mike. This was really interesting. I have absolutely no STEM background, so it was all for me very, very mind-blowing, really interesting stuff. Thank you. So we have some questions that came in. One of them was about the Citizens Science Project. How can people get involved in that? Is it open to everyone? Do you have to have any particular training?
It's open to everyone, for sure. The most well-known one is Aurorasaurus, which is a rather wonderful name. So if you look up Aurorasaurus, they're very organized. They have a good checking system. It was part funded by NASA. Hopefully it still is, and the NASA cuts haven't got to it. But it's very, very well organized, and it's run by a group, and they write papers on statistics from the data and stuff, and credit all the people that have contributed. But there are others. There's one in Finland whose name I've forgotten. Yeah, I should remember, but it's very good, but that's very Finland oriented. And then actually on the events that cause it, the coronal mass ejection, there's something called Solar Storm Watch, which is run from Reading here by the people that watch out for. We have an instrument on various satellites, particularly stereo, where we predict which we use to predict these things coming. And we're finding that citizen science are really good at identifying. And we've had several of those citizen scientists have become co-authors on our papers and things like that. So that's called Solar Stormwatch, and it won Citizen Science Project of the Year at the Web Awards about a decade ago now, but it's still good.
Excellent. Thank you so much. Just to, you're still sharing your screen, Mike. I don't know if you want to try
Oh, okay.
switch
Yes, I
off
can
the
get rid of that.
sharing.
Sorry.
But we only have 9 minutes and it will literally kick us out. So I'm going to give you a couple more questions that you
Oh,
can hopefully answer. So the first records begin in kind of official records from the 1650s. Is there anywhere anyone can find any older records or maybe even kind of ancient reporting where they can see any reports of auroras, and where would they be able to find them?
Yes, there are some, and there are some people that actively pursue them. I mean, my old boss at the Rutherford lab, a very nice man called David Willis, who sadly died a couple of weeks ago. But Dave was passionate about hunting down, and used to find a lot of ancient Korean observations and things like that. And China is a fairly untapped source for this as well, largely because Western people couldn't read Chinese script and things like that. So there are new ones crop up every so often, but they're very isolated. The nice thing about 1650, since 1650, is a lot of people have been observing and chronicling them, and so we have a reasonable sample. When you go back before that, it tends to be isolated events, maybe one every 30, 40 years or so. So that's why we decided to start at 1650. That's when the number really picked up.
Okay, thank you. That's really interesting. Right, another question is, in terms of where is the best place to see, you obviously said it depends on where you are in terms of latitude. But let's say if you are in the UK, where would be the best spots in the UK to observe the events?
Okay, well, obviously, cloud is your enemy. People should beware, by the way, in the UK. Another problem that we have recently is pink glows in the sky that are actually greenhouses, because people use these LED lights. There's no point in shining green because plants only reflect it. So they use blue, a mixture of blue and red, and so you get a pink glow in the sky, particularly if it's cloudy. So that's another problem. People think they're seeing aurora, but it's not. Um, Really away from street lights, where cloud cover is lower, so that tends to favor the east coast over the west coast. Um, uh, and the further north you go, the higher your chances are, quite frankly. So, and if you're really keen, get yourself to Shetland or Orkneys, or on a flight to the Faroes. A good friend of mine is head of tourism for the Faroe Islands, so she
Maybe
would
we
thank
can
me
share
greatly
that
if
in the
I.
follow-up
Yes,
email.
yes.
Another question is more about our courses. So if you were to be an undergraduate or a postgraduate student at Reading, would auroras would be looked at as a subject? Are
Yeah,
there any modules?
yeah. Yes, but we have a meteorology, we have a module. By the way, the reason I'm in a meteorology department is that we're using meteorological techniques in space weather now, as well as terrestrial weather. Yes, we run a space weather module that explains aurora and quite why the Carrington event has such disastrous effects on the telegraph system, and what can happen nowadays, which is much. There are many more systems now that are operational systems that are prone to space weather. And so, in fact, it's actually up there with pandemic flu on the national risk register nowadays, is space weather events. And so it's a very active and important field. So, and yes, we run a course on it for people as part of a meteorology degree.
Thank you. Okay, I think that was the last question from our audience. Thank you, Mike, for your time. This was really interesting. I really enjoyed it, and I'm sure everyone else did. Everyone who joined has stayed on for the whole duration of the webinar, which just shows that everyone was really interested. thank you so much to everyone who attended today. Thank you to Mike. The recording will be shared after the event, so if you want to go back and rewatch anything, please feel free to. If you have any questions, you can email us on outreach@reading.ac.uk. But that's it. Is there anything you wanted to add, Mike?
No, and also people can email me directly on my Reading email. Yes. Oh, I should have said when the equinoxes are best. So September or March for aurora hunting. Not summer because of the sunlight, and the further north you go, that gets to be a bigger problem. So not summer, but it doesn't have to be midwinter. And in fact, the equinoxes are better. So yeah.
So the equinoxes, the March one is on 21st of March. So mark your calendars and save the date.
It doesn't that's plus or minus a month, but it does peak near the two equinoxes. So yeah. And watch Huck's Tea. All the people that do auroral tourism up in the Tromsø area, they all have Huck's Tea on their phones so that they can see when they can judge where to go to find it. So that was quite nice. I like that. So yes, we're helping the tourist industry.
It's quite a community, isn't it? I'm sure there's a whole Reddit threads and people just creating groups to hunt together and travel together and keep the records. So
yeah.
There's a lot of information online.
It was interesting because our study, we found auroral sightings went right down, and then because of camera and social media and phone cameras, it's gone right up again now. So it's a very good fit. We're getting nice lots of sightings. In the 60s and 70s, it got quite bad. That was the worst recording for 300 years in terms of aurora. People just didn't bother. So, but now they do.
It's complete opposite of what happened to all the sightings of UFOs with the development of phones. They just all went down and no one saw them anymore.
They don't like to be photographed.
Whereas auroras, they do. They like to show off.
Yes, they do, yes.
Okay. Yeah. Well, thank you so much. Thank you, everyone. Thank you, Mike. Really appreciate your time. Really enjoyed this. And we will finish the recording here. And if anyone wants to get in touch, please feel free to get in touch with us.
Bye all. Thanks for listening.
Bye.